Okay, I'm back, and it's question 3.1. So, complex pollutants, ones that aren't uniformly mixing, or cumulative, other more complicated qualities with the pollutant. And 3.1, what's the problem here? Basically, for some reason that's not explained, we've got two sources, one in the west and one in the east, and there's a recipient in the middle. And the regulator only cares about what happens here. And sometimes the wind blows stuff in from the west, and sometimes it blows stuff in from the east. So the probability of blowing in this way is P. The probability of blowing in that way is 1 minus P. And here we have abatement AW, and here we have abatement AE. And again, for reasons not explained, the regulator has a target for effective abatement at the recipient, rather than, for instance, a target about environmental quality or so on. Part A. Yeah, and that a target is A star should be 30. So part A, what's the constraint in the regulator's cost minimization problem? So this is a benevolent regulator, so to speak, determined to reach this target, but apart from that, wanting to minimize the total firm costs. So what does this target mean? It means that P times AW plus 1 minus P times AE should be at least 30, doesn't it, I think? I'm going to pause there and try and find a better pen. Okay, hopefully brand new pen. So, part B, determine the cost-effective abatement level for the two emissions sources. So, basically what this means is that we want to achieve this target, or this, we have to satisfy this constraint while minimizing costs. So the problem is, if you like, the problem facing the social planner who's going to tell, because we're not told about any instruments here, so let's just think of a social planner just telling these emitters what to do. And that benevolent social planner wants to minimize total costs through choice of AW and AE. And total costs are equal to the sum of the top of the two different costs, aren't they? So this is seriously straightforward. 50 AE plus 2 AE squared plus 100 AW plus 3 AW squared. Okay, subject to that constraint. So, a necessary condition for this to hold is for an internal solution is if we set up a Lagrangian and say minus lambda or plus lambda, doesn't matter, PAW plus 1 minus P AE minus 30. So obviously we're never going to have more abatement than 30, so we can put an equality sign here, and then this is Lund-Gromachet. And this has to hold for an internal solution. It's not a sufficient condition. In theory, we should be double checking that this solution we find is actually the best solution. But let's just find the solution. So we're going to take first order conditions in AE and AW, aren't we? So the first order conditions in AE, what do they give? They give 50 plus 4AE minus lambda 1 minus P equals 0. And the first order condition in AW gives 100 plus 6 AW. So why do we do this? Equals lambda 1 minus P. And here we have 100 plus 6 AW minus lambda P equals 0. So equals lambda P. Now we can divide one by the other and then bring things around, and we're going to end up with 50 plus 4AE equals, dividing one by the other, 1 minus P over P. And then this has ended up on the bottom line here, but we're going to bring it up, times 100 plus 6 AW. Okay. So this is a necessary condition for an internal optimum, but we've got another equation in AW and E, haven't we? Which is this one. PAW plus 1 minus PAE equals 30. Let's get rid of this, because we know it's going to be satisfied with equality. So two equations and two unknowns, and a bit of a messy problem to solve. Let's see if we can do this. So we're not told P at all, are we? We want to solve this. Yeah. We're going to solve, we can't simplify this anymore. So we've got a nice simple term in 4AE here. So let's rewrite this to get a term in 4AE there. So let's divide through by 1 minus P and multiply by 4. So we've got 4 P over 1 minus P AW plus 4 AE equals 120, 4 times 30 over 1 minus P. So now let's subtract the subtract this from this. Okay. So we start with this. We've got 4P over 1 minus P AW on the left hand side. Then we've got plus 4AE minus 4AE minus 50 is equal to this 120 over 1 minus P minus this minus 1 minus P over P 100 plus 6 AW. we going to simplify this? We want to get rid of these 1 minus p's from the bottom line, I think, don't we? We can do that for starters. So we've got 4p AW minus 50, 1 minus p equals 120 minus 1 minus p squared over p 100 plus 6 AW. We also want to get rid of this p from the bottom line, so let's go through that as well. 4p squared, 50, 1 minus p, 120p minus 1 minus p squared, 100 plus 6 AW. Whew. Okay, so let's collect terms in AW. So we've got AW times 4p squared minus, coming over is plus 1 minus p all squared times 6. So that's plus 6 times 1 minus p all squared is equal to collecting terms that aren't in AW, 120p minus 50 blah blah blah, so that's going to be plus 50, 1 minus p times p minus 1 minus p squared times 100. Okay, let me just have a quick check of this. So AW 4p squared 6 1 minus p squared, and then 120p plus 50 1 minus p minus 1 minus p squared times 100. Okay. I don't think this is very exciting. I'm going to pause this while I do the next line, and then I'll just show you the working afterwards. Okay, I had a quick think. Just looking at this, taking a step back, the first thing we can do is divide everything by 2. Okay, so divide through by 2 just to simplify very slightly. I'm going to do that first, which gives this equation. Okay, so I've gone through this now. First we divided by 2 to get this, then I've multiplied out this and this and put the terms together, and we end up with this, and then we simply divide through to get this. Then to find AE, we need to put this back into here. And of course, it would be absolutely fine to express the answer in terms of AW. Just say AE is 30 over 1 minus p minus p over 1 minus p AW. And we know AW, so that would be fine. But this is how it pans out if you actually work it out. Okay, I'm going to pause again and look at the next part of the question. Okay, final part of this question, part C, identify cost-effective charges to be imposed at the 2 emission sources. So what are these charges? Well, let's assume it's an emissions tax. It's a bit vague, isn't it? So how are we going to, the question then is, what tax do we need to achieve these limits? And we know that through the tax, the firms will do this in the sort of cost-effective way. So how can we model this? If we're going to do it really carefully and thoroughly, we need to think about the firm's profits. So let's think about the Western firm's profits pi W, which are its baseline profits, pi W0, which is just a constant, they're given, minus any payments it has to make for its emissions, which will be TOR, the sort of tax rate, times its emissions, which are going to be baseline emissions. Sorry, that's an E, isn't it? EW0 minus abatement. That's how much the firm is going to have to pay if you impose a tax. And the other thing which is coming into the profit function is the actual costs of abatement, which are 100 AW plus 3 AW squared. So that's minus 100 AW minus 3 AW squared. And then we need to think, okay, we've got to find the level of the tax to achieve this level of emissions. How do we find that? We take the first order condition. In AW, what do we get? This is just constant. This is also constant, but here we have plus TOR AW. So when we take the first order condition, we get TOR, and then we've got minus minus equals naught. So we can shift those across and say TOR equals 100, again, minus, and then we shift it across, it's plus 6 AW. And of course, we've got AW here. If you wanted to, you could call this, if you want to be really careful with your notation, you could call this like AW star or something to make it super clear, and then this will be 100 plus 6 AW star. Okay, the equivalent expression for the Eastern firm, pi E naught minus TOR E naught E minus A E minus 50 AE and 2 AE squared. So the first order condition gives TOR, yeah, so this should be TOR W, shouldn't it? And this should be TOR E. The first order condition gives 50 plus 4 AE. Okie doke, just check my crib sheet. Yep, we're doing fine. You're asked to comment on this. Wow. So how do you really comment on this? You can't, because these expressions for AW and AE are so complicated. So to comment on this, we really want to know, are these two paying different tax rates? Which you would generally think they would do if these probabilities differ. If the probabilities are the same, they should end up paying the same tax rate, shouldn't they? So what we really want to do is say, let's look at TOR W divided by TOR E. And if we do that, we will actually find, amazingly, after a lot of algebra that I'm not going to take you through, but we will find that TOR W over TOR E is P over 1 minus P. Okay. Which is kind of neat. And it's of course what you'd expect. So if P is 1, 1 minus P is 0, you're only going to tax this guy. If P is a half, the taxes will be equal. If P is 0, you're only going to tax this guy. It makes total sense. Okay. End of question 3.1.